want to now talk about is the process of or interference between, let's say, virtual reality and eye motions, right. So, what happens at this kind of interface? What are some of the problems that arise? So, regarding virtual reality and eye motions. So, let me just list off all of the problems I can think about now that we have enough understanding. So, number one is I have the screen like I drew before. I have the lens in front of that. So I have the lens in front of that. I have the eye before that. And the pupil though, and let me just draw the cornea part here, may be aimed at the top part, right, so that so we're looking at, let's say, some pixels that are on the top part of the screen here. So that means that you're not looking directly through the optical center, the central axis here of the optical system. So even if you put the lens, right, so maybe when you put on the headset, the lens might be perfectly centered over your eye, but when you look out of the sides, you're looking out of the extreme parts of the lens, right, close to the boundary of the lens. If you remember the aberrations that we talked about a couple of lectures ago, the problems are greater at the periphery. So now you have greater chromatic aberration to deal with, you have greater optical distortions, we have this pincushion distortion to deal with. There may be issues of the focal plane changing a bit due to spherical aberrations. Maybe you can compensate for that with your eyes, but probably not if it's already at infinity. You'd have to move it so that your eyes have to do the extra amount of work to converge. If the distortions around the periphery due to spherical aberrations cause the rays to be a little bit converged, then it's already going to converge before your retina, and there's nothing your lens can do to fix it in your eye. So these are the kind of problems you could have by looking out of the side. So there are problems, as I said, of focal plane or just optical distortion. If there's distortion, I could try to compensate for the optical distortion in software, but the distortion I get could be a function of where I'm pointing my eye directly. So it's very hard to compensate for that because the pupil is translating back and forth along a circular arc as it's trying to look at different places here. So that means that in principle what I would like to have is some kind of software based distortion compensation function where I calculate a barrel distortion, as I mentioned a couple of lectures ago, and I would like to have that be dependent on where exactly the pupil is at, but if I do not have an eye tracker then I don't know where that is. So I have to calculate a one distortion fits all situations, which means that inevitably there's going to be some bad distortion problems with a simple lens like this. So there seems to be no clear way out of this problem. And if that's the case, if you see distortion in your periphery and then you start moving your character around in VR, or you just do simple motions that correspond to your natural head motions. And let me say not move the character, but you just do motions in VR where you're perfectly matching your head motions. If there's distortion at the periphery, then the accelerations you're perceiving in VR because of the distortion might not match what it would be in the real world. And you could get nauseated just from that. So there's a lot of interesting problems coming in here just from this off-axis looking through the lens. So that's a huge problem. Very, very big, annoying problem. Number two, VOR gain adaptation. I already explained that one. Which again is related to these distortions. So the vestibulo-ocular reflex will nicely learn some different gain that compensates for you, but it may cause more fatigue and it may cause you to have the wrong gain when you re-enter the real world. and then cause the world to seem like it's swimming around incorrectly, to cause objects to not look stationary. 3, there's the complicated interface between the display and the photoreceptors. I think I suggested before, if we're going to make the display this close, why don't we just go all the way in and just send the right signals to the optical nerve, right? Or just, you know, kind of cut the photoreceptors a bit and just give them whatever they need and directly control that, right? So we don't want to damage the human eye like that. So we have to deal with this, the unfortunate complexities of the output pixels being on the display and the input pixels being along the retina, being called photoreceptors, and they all have their peculiarities, and that causes a lot of difficulty. So for example, the pixels on the display switch their color or intensity at some non-zero rate. In other words, it's not instantaneous. If it's an LCD display, it could take up to 20 milliseconds to switch. If you're running at 60 hertz, how long, what's the time between frames if you're running at 60 hertz? So 16.67 milliseconds. So it could take longer than an entire frame just to switch the pixels. So if you're using your vestibulo-ocular reflex and you're trying to perceive something as being stationary, you're actually jumping from pixel to pixel. The object will be jumping from pixel to pixel. The pixels are gradually changing. It will cause the object to smear. If you use something like an OLED display, which has very fast pixel switching time, say on around 80 microseconds instead of up to 20 milliseconds, then you'll have less blurring, but you may have other problems, which I will eventually get into in the class. It's just something to pay attention to. The real world doesn't have that problem, only the display does that's in front of your eye. There's RGB subpixel structure. Some of you were trying this during the break. We were taking a close look at displays with magnifying lenses, so I encourage you to try that on your own time. You do not simply have simple dots or simple rectangles with RGB. There are sub-pixel patterns of individual R's, G's, and B's arranged together. Sometimes they're in a nice regular pattern. Sometimes there's some irregularity. There's always regularity at some level, but there's some kind of interesting patterns inside. That's about all I can say about it at this point. So that has to be dealt with. Frames might be off, in other words black, at particular times. So in other words, the entire display may be black for some period. So if you have a slow switching display like an LCD, it may never go black. You're just always switching between different colors and intensities, and it's just barely keeping up, let's say. But if you have a very fast switching display, for some reasons that I'll explain when we cover perception of motion, you may want to pulse it on and then turn it off, and then pulse it on and then turn it off. So the display will be black a lot of the time. How does that affect your brain? How does that affect your photoreceptors? Something very interesting we should talk about. CRT displays had this problem as well, because the phosphors would go dark very quickly. D, asynchronous, or I'll say line by line display scan out. So displays typically change the pixels in some kind of ordering that's sequential. maybe asynchronous, maybe a better word there would be sequential. So it's going along sequentially. You'd like to just change all the pixels at once. Instead, they're changing in some kind of organized way that looks a lot like the way old CRTs worked by controlling the electron beam and just scanning it line by line. So that mentality has been around for a long time. So the real world doesn't act like that, but this display in front of your eye does in most cases. So it needs to be re-engineered. Let's see what else is going on. E, your photoreceptors, so the input pixels, are actually quite slow to respond. It takes them about 0.1 to 0.2 seconds to respond. All right, so isn't that interesting? So 100 or 200 milliseconds to respond. And finally, all the eye movements, especially with microsaccades. Some eye movements are designed to improve stability. Some don't seem to exactly do that. All of the movements must be causing at least a little bit of shift. They cannot be perfect. So eye movements and object movements as well shift the image on the retina, while you also have very slow photoreceptor response. So by some amount. It cannot be perfect. So all of these are going on due to this complicated interaction between the display and your photoreceptors. Right? So that needs to be taken into account. I don't think all of these are fully understood, right? And the more you understand about this, the better you will do if you get into engineering, especially the hardware side, computer engineering and hardware side of virtual reality, including the optics. All of these come together, right? So groups of people need to work together to solve these kinds of problems who normally don't work together, right? So people who understand the physiology, neuroscience, neurobiology of human vision, computer engineering and optical engineering all together in one place here to resolve this interface, right? Many different possible designs in here. I could replace the screen with a small retinal projector if you like, but you still have many of the same kinds of issues, right? Maybe some improve, some get worse. Interesting trade-offs there. I have one more, so I'm 1, 2, 3, so I have one more case. This one's really problematic. Is that vergence is usually in the real world coupled with accommodation. Remember that accommodation means refocusing, and vergence means convergence or divergence. That's these motions that you do for stereo correspondences, right? So in the real world, and again this is for younger people, when you bring an object very close, your eyes are converging towards it, and then they are also refocusing the lens. So those muscles are tightly correlated, tightly coupled, almost like when I move all the muscles in my hands together to grasp something. I'm not really thinking about the individual muscle movements. So these are very tightly coupled. If I put the display in front of the eye like this, and I put the lens at the appropriate distance so that the rays coming out of the display through the lens are parallel, right? So if I go ahead and I do this, then everything on the display is in focus always, regardless of my perceived depth, right? So that means that this display is training you, this head-mounted display is training you to separate vergence from accommodation. So it's telling your brain, no, you don't need to do that anymore. So if your brain is accustomed to doing that, then you may unintentionally blur the objects that are close up because your brain's trying to focus on them, and eventually we'll learn to separate those. The same thing happens if you're sitting at in a movie theater watching 3D movies. It's again designed where everything is in focus, even if in stereo it's very close up, and that's motivated the movie industry to increase the depth of things that are three-dimensional in the movie. So the objects are actually further back typically. They're not on your lap. They tried that for a while and there were a lot of complaints of discomfort. So people may feel fatigued from this because your brain's learning a new trick and having to maintain this. It's separation of divergence from accommodation. So the muscles are now getting separated in some way. It's like giving you some new degree of freedom that you didn't know you had.